All right. 3.3, back to chapter 3. So today we're going to talk about two different models. The book talks about a few others. These two, I think, to me, are the most accessible. The first one is our linear model. And we're going to talk about Newton's law of cooling. So the idea here for a system is we're imagining that we have two semi-cylindrical tanks of water, and we join them, we put them together on a diameter. So if we're looking from above, we have something like this, and here's tank 1, and here's tank 2. X1 and X2 are the temperatures in the tanks. So these are, if we wanted to imagine that these are two containers of coffee. And we're assuming that the outer perimeter is perfectly insulated. So no heat escapes, no heat crosses the outer boundary here. So this is perfect insulation. So if these two tanks start at two different temperatures, the water in them are two different temperatures, Newton's law of cooling is going to apply to each tank. But the temperature, the rate of change of the temperature in this tank depends on the temperature in the other tank. And the rate of change of the temperature in the other tank depends on the rate of change of temperature, depends on the temperature in this tank. So we have a system of differential equations. We're also assuming some other assumptions that we make is that the temperature in the entire tank, the tank is small enough that the temperature in the entire tank at any particular time is constant. So if it changes, the entire tank changes at once. So otherwise we'd have to model with a partial differential equation where we have the temperature changing in time and with respect to distance, which makes it a little more complicated. We'd need a little more stuff in order to do that, but not a lot. And I'm going to assume, just for simplicity, that that the proportionality constant is 1. So the temperature, the rate of change of the temperature in one tank is just going to be proportional to the difference in the temperatures between the two tanks. So I'm going to write dx1 dt, and I want to make sure I get since my proportionality constant is 1, I want to make sure I get put these in the right order. So if x2 is higher, the temperature in x2 is higher than the temperature in x1, we would expect the rate of change to be the temperature to increase. So I'm going to say x2 minus x1. So if x2 is higher, we expect the rate of change in this tank to be positive. And then dx2 dt would be x1 minus x2. And there's a pretty simple linear system of differential equations. And I'm going to say that x1 of 0 is just T1, and x2 of 0 is T2, some initial temperature in our tanks. So we have a nice, simple system of differential equations. So there's one application of a system of differential equations using a physical law, I guess, that we're somewhat familiar with. Solving the system of differential equations is problem number 1 in the homework. But I want to talk about the solution. Talk about how we think this is going to come out for a second. So, just based on what's going on here, eventually, what would you expect to happen to the temperatures? They'd be the same, right? Eventually, after a long time, they'd be the same. And what would we think the temperature should be? The average of the two? Because we have the temperature changing back and forth. Yeah, we're assuming they're the same. They're the same materials. Whoever brewed coffee X1 brewed it at the same strength as coffee X2, and they use the same method. So one's not French press that has a bunch of stuff in it, and the other's not ultra filtered. And before eventually, what do we think that? How do we think the eigenvectors are going to come out here? So what's going to happen in the meantime? How is it going to behave? Like right when we start measuring. How do we expect them to heat or cool?
Negative exponential.
Negative exponential? Might be a good. So if we, so when we solved Newton's law of cooling before, what kind of solution do we get? We got an exponential solution, right? Newton's law of cooling gives us a separable differential equation where we end up with an exponential. So we expect that our solution should come out to be that the eventual temperature is the average of the two temperatures. And in the meantime, we should have some kind of negative exponential term where the temperature in one is decaying slowly over time. So keep that in mind. We'll solve this system as part of our homework. But that's one model. I also the second homework problem is Newton's law of cooling, but so this is homework number 2. This time we have what the scenario in this situation is this. So we have 3 tanks that are joined to form a cylinder. So yeah, we end up with a 3x3 matrix. So what I'm going to say here is when you set up your system, be careful with how you set up your subtraction. If you get a positive exponential, you get a positive eigenvalue, you set your subtraction up the wrong way. Because you shouldn't get exponential growth in the temperature in any of the tanks. So that's homework problem number 2. What's that? It's going to get warmer, yes. You'll see. All right. So our second model that we're going to talk about, that I think is relatively accessible, is a predator-prey model. Oh, and before we talk about this, I wanted to go back to Newton's law of cooling. A similar scenario to Newton's law of cooling is radioactive decay series. So often, usually, a radioactive material will decay into another radioactive material, and that material will decay. And so you get a kind of a chain of radioactive decay. And we know that for radioactive decay, the rate of change of the material is proportional to the amount of the material. So if a radioactive material is decaying into a second material, well then the amount of that material is changing, but the rate of change of that material is proportional to the amount of that material. So you get a situation similar to this, where the two derivatives are linked, because as one changes, it increases the amount of the other one. Our book talks about the radioactive series, if you want to look at that, but it's similar to Newton's law of cooling. Predator-prey model. So what we're assuming here for the predator-prey model is that we have only two species. And they interact in some area. And the other assumption for the predator-prey model is one species is they're herbivores. Is it V-O-I-R-E or just V-O-R-E? One species are herbivores, the other eats only the first species. Our book uses foxes and rabbits as the predator and prey. So if x1 of t is the predator population, and x2 of t is the prey population. If there are no prey animals, we would expect the rate of change of the predator population to be proportional to the population, classic population model. And we'd expect the rate of change to be negative because those predators don't have any food. So without prey, we expect dx1 dt to be negative a times x1, where a is some proportionality constant. Negative because these four predators don't have anything to eat. And we're saying a is less than 0. And with prey, we expect the interaction to be jointly proportional to the populations. So proportional to x1 times x2. And this should tend to increase the predator population because they have food. I'm just going to write dx1 dt should be jointly proportional and there are other assumptions you can make. This is just a simplifying assumption. So we would say, in that case, dx1 dt equals negative ax 1 plus b x1 x2, where b is greater than 0. So the negative, because we expect some aspect of the population to be to follow an exponential model. And then we get this x1, x2, the interaction term, where our population is increasing because the predators are eating. All right, now let's talk about the prey. In the absence of predators with unlimited food, we expect the prey population to grow because they're just running around eating and repopulating. So we would say dx2 dt equals dx2, where d is greater than 0. We'll use c next. And then with predation, we expect the interaction between predator and prey to decrease the prey population. dx2 minus cx1 x2. I did it this way to be consistent with what the book did. I don't know why they use C and D in this order. So we have a system of nonlinear differential equations. Oops, I need to plug in here. So we have dx1 dt is negative ax1 plus bx1 x2, and dx2 dt is dx2 minus cx1 x2. This is a classic predator-prey model. This is the Lotka Volterra predator-prey model. And depending on the values of A, B, C, and D, we can, even without solving it, we can tell by looking at the equations which variable should represent predators, which variable should represent prey. We can tell by the size of the interaction term, the relative populations of the two. So you can get a lot of information without solving these, but we can't solve these in terms of elementary functions. Yes?
What's the difference between the two equations? What do they represent?
So this one, without the interaction term, the population is decreasing. With this one, without the interaction term, the population is increasing. So we expect the predators without prey, their population to decrease because they're not eating. We expect the prey, we're assuming that they're herbivores, there's plenty of food around, so without predators, their population increasing. The interaction here for the prey increases their population. The interaction for the predators, for the prey, for the predators, the interaction should increase their population because they're eating. For the interaction for the prey, the interaction should decrease the population because they're eating. And then there's less of them, also less of them to reproduce.
Would B and C not just be the same?
They could be. But if you had, say you had a very large predator and small prey.
Okay.
So one predator, so one coyote can eat a lot of mice.
Okay.
So that would be the difference in the B and the C. But like mountain lion trying to get a deer, then it takes a lot of work for the one mountain lion to get one deer, and the one deer feeds one mountain lion for a longer period of time.
Okay.
All right, so this is our first predator-prey model, the Lotka-Volterra model. We can also kind of modify this. Instead of predator-prey model, we could talk about a competition model. And it's really not a different model, it's just a modification of the predator-prey model. And in the competition models, the two populations compete rather than, they compete for resources. But they don't, one doesn't consume the other. So they compete for resources, so we might have a couple of herbivores in some habitat. They're competing for the food. We might have several predators in the habitat, and they're competing for the prey. So in the absence of one or the other, we expect, in the absence of competition, we expect either one of the populations to grow. So we'd say the rate of change of the one population, dx dt, is ax1. It's going to increase. And the population of the other the rate of change of the other population is going to increase. And with competition, if there's some interaction between the two, so, I don't know, chasing each other away from the prime resources, whatever, we would expect the interaction to decrease the population of either one of them. So our system becomes dx1 dt equals ax1 minus bx1 x2, and dx2 dt is cx2 minus dx1 x2. We might also just expect, with the presence of another competitor, the population of one or the other would decrease. We could say dx1 dt equals ax1 minus bx2. Just the presence of the competition is bad for the population of the other one. So two different competition models there. One where we have an interaction between the two. One just the presence of one or the other. And this model would be actually a linear model. This model is nonlinear because of these multiplied terms here. And then finally, we saw in the last chapter that another model for population growth is the logistic model. And that's where the relative rate of change is a function of the population. The relative rate of change was the rate of change divided by the population is some function of the population. And the logistic model is when that function was linear. So if we have competition with logistic population growth, we would have dx1 dt equals ax1 minus bx1 squared. That's the logistic model where we have the squared term. This is what we talked about at the end of last chapter. Minus our interaction term, cx1, x2. And then our other equation would be similar. I'm going to make these all 1s and then make these all 2s. a2, x2 minus b2, x2 squared minus c2, x1, x2. And we could also add a logistic term to the predator-prey model if we wanted. Which would probably, logistic growth is probably a more accurate description of population growth in general, so it's not unlimited exponential either way. So what we do in the homework with these nonlinear models is you're just given a model, I gave you a model, and some initial conditions, and then you're looking at the solution curves and talking about the form of the solution. And I asked you some questions about the comparison between the two competition models. There's one predator-prey model in here that you look at, and then there's two competition models with different values of your constants. And you have solution curves for different initial conditions that you look at and kind of analyze qualitatively. And then I ask a couple of questions about those. So the only really analytic part of this homework is the Newton's law of cooling portion. And I wanted to go back to the predator-prey model for this system. Other than we can find the equilibrium solutions, so we factor out an x1 and an x2. I forgot to write that down. So our equilibrium solutions here. So here we'd factor out an x1, here we'd factor out an x2. Our equilibrium solutions are x1 of t equals 0, x2 of t equals 0. So we have no predators or no prey. That gives us an equilibrium solution. And x2 equals a over b, and x1 equals d over c. Those would be our equilibrium solutions. So in that case, then we have a steady state solution. Other than that, we can't solve this predator-prey model in terms of elementary functions. All right, and this, I wanted to do this section because it kind of a little bit touches back to what kinds of things we can actually do with these systems of differential equations, and just thinking about the physical situation and how we relate a derivative and other functions and how they get combined in specific ways. All right. I like to call it a problem set instead of a solution, instead of a worksheet. It makes it sound a little fancier.